All right, everyone, we're going to get started. So today we're going to have kind of a theoretical component to the lecture and a more practical component. So the theoretical component will be finishing the lecture from last week. The more practical component will be a tutorial that Kelvin will give on TensorFlow. So hopefully all of you have already downloaded the materials for homework 1. You've taken a look at it. Some of you might already be familiar with TensorFlow, in which case great. But if you want a refresher, or if you haven't worked with TensorFlow before, definitely stick around for the second part of today's lecture, where Kelvin will give a tutorial on TensorFlow. But first, I wanted to take a little bit of time to finish some of the derivations from last week that we started on. So as a quick recap, we talked about imitation learning. And we talked about how we can do regular behavioral cloning, which basically amounts to taking a data set of observation action tuples and just running supervised learning on it. And we saw how, in theory, it shouldn't work, but in practice, in many cases, it does work. And then we talked about some algorithms that can, in theory, make it work more consistently, like, for example, Dagger, which relabels data collected using the policy with optimal actions from the expert, and at convergence drives the observation distribution for the training set to be the same as the observation distribution under your current policy. So at the end of the lecture last week, we started developing some theoretical tools that we can use to more formally quantify how bad behavioral cloning is, and also maybe to help us understand why things like Dagger are actually helpful. So what I'm going to do today is I'm going to recap the basic derivation that we saw with the tightrope walker at the end of the lecture last week, and then I will present a more general derivation, which is the one that we actually use to analyze these sorts of algorithms. And some of the tools that we'll see there will actually come up again later on when we discuss things like more advanced policy gradient methods. So here we'll use those tools to analyze imitation learning. Later on, similar tools will be used to analyze reinforcement learning methods. OK, but let's start with the recap. So we saw this intuition last time that the reason that behavioral cloning might not do so well is that when you fit your policy to your training set, your policy will not be perfect. It will make maybe some small mistakes. And when it makes a small mistake, it will deviate from the states that it saw during training, and will find itself in a state that's different than any state that it was trained on. And if it made a small mistake in states that are similar to its training states, it might make a slightly bigger mistake in states that are different from its training states. And then it might find itself in even more strange and unusual states, where it might make an even bigger mistake. And these mistakes might build up gradually, so that by the end of a really long trajectory, you might be doing something very peculiar. So with the car, if your car is veering a little to the left, it's never seen an image where it's veering to the left. Now it veers even more to the left, and eventually it goes off the road. Now that's the intuition. To more formally kind of quantify how bad it is, we introduced a little bit of notation and some assumptions. So we said that this trajectory is capital T time steps in length. And we're going to try to quantify the goodness of a imitation learning policy in terms of this 0-1 loss. So the 0-1 loss, very simple. It's just counting the number of mistakes you make. So it says you don't really care about whether you're in a good state or bad state. All you care about is whether you did the same thing as what the expert would have done. So for the car, going off the road is not actually the problem. The problem is that it did things that a person wouldn't have done. So the 0-1 loss, basically, you get 0 loss if you take the action that the demonstrator, that the human would have done, and a loss of 1 if you take any other action. It's a very simple model. It's not the only model we could use. We could have a more structured loss. We could capture the fact that some actions are similar to others. But this is the simplest one to use in the analysis. And then we need some assumption. We need some assumption that says, like, learning basically works to some degree. Because if learning didn't work, if the supervised learning process just resulted in a random neural net, then all bets would be off. So we need some kind of reasonable assumption on what the learning process actually does. And the first assumption, the assumption we work with on this slide, is that when you train on a state, if you actually saw, so this is for all the states in your training set, if you actually saw that state and you saw what the person did, then your probability of taking the wrong action would be less than or equal to epsilon. This is not a very strong assumption. This basically says you can memorize the data. And in fact, it doesn't even say you can memorize the data perfectly. It just says your probability of making a mistake on your data is at most epsilon. Very, very simple assumption. We'll see a slightly less naive assumption on the next slide. OK, so this is the assumption. this is the loss, length is capital T, and we introduced a particular environment, right? So what we're after here is we're after a bound. We're after a worst case bound that says even if everything goes as poorly as possible, so long as this assumption is satisfied, what will be your total loss? So to analyze that, we want to sort of construct the worst possible situation and then study that. So the worst possible situation that we came up with is this tightrope walker. And semantically, this might be a little bit misleading because this is a very strange tightrope walker. It's a behavioral cloning tightrope walker. So he's not concerned with falling because he's afraid he's going to hit the ground. He's concerned with falling because he's going to incur 0-1 loss. So he's afraid that if he falls off the tightrope, he will not know what actions to take to match the human expert because the human expert never fell off the tightrope. So we can sort of schematically represent this situation as this kind of grid world where all of the demonstrations followed along on this middle path, so they all stayed on the tightrope. And there are these states that involve falling off the tightrope where there was no data. So D-train here just consists of these gray states, and these red states are not in the training set. And then the quantity that we're concerned with bounding is the expectation of the total cost. So this is a sum from 1 to capital T. The expectation is taken with respect to the policy, and we want to come up with a bound that says this total, the expectation of the sum will always be less than or equal to some quantity. And that quantity will, of course, be expressed in terms of capital T and epsilon. OK, does anybody have any questions about the setup for this derivation or the assumptions? This is very important because if there's some confusion about the assumptions, then the rest of this won't make any sense. So please raise your hand and ask if you have any uncertainty about the assumptions or the setup. Yes?
What's epsilon?
Yeah, so what's epsilon? Where does it come from? So epsilon is the probability that your learned policy makes a mistake on its training data. Now, where does the value of epsilon come from? Well, the value of epsilon essentially captures the strength of your learning method. So if, for example, the policy is trained with like logistic regression with some very, very bad features, maybe epsilon might be very large because your logistic regression might just underfit. But if you use a big neural net that's very powerful, that can capture lots of different functions, then probably epsilon would be very, very small. Crucially, epsilon has nothing to do with control, nothing to do with temporal sequences. It's purely a way to quantify the strength of your supervised learner. Any other questions? OK, so let's start going through this derivation. And the way that we're going to estimate the expected value of this sum is we'll basically go through the sum one term at a time. So in the sum, there's a cost of the first time step, a cost of the second time step, a cost of the third, etc. And remember that your cost is 1 if you make a mistake and 0 otherwise. So on the very first time step, you're standing right there. You're just about to start walking across the tightrope. You're in a state that you saw in your training set, which means that your probability of making a mistake is epsilon. Now, if you make a mistake, right, the demonstrator went to the right. So if you make a mistake, you're going to go down or up. Once you've made that mistake, you fall off the tightrope, which means that you will never again see any state that was in the training set. So once you've fallen off the tightrope, you might basically make a mistake every single time. You have no bound at that point about how likely you are to make mistakes. So that means that on the very first time step, there's a chance, a probability epsilon, that you fall off. And after that, the sum will be capital T. So once you make one mistake, you just make mistakes forever. If you don't fall off, then you have 1 minus epsilon. That's your probability of not falling off, the probability of taking the right action. So with probability 1 minus epsilon, you go to the next state, which is in your training set, and then basically the same exact thing happens. So at that second state, you again have an epsilon probability of falling off. You have only t minus 1 steps left. So now the total number of mistakes will be t minus 1. And then the same thing repeats again. So then you have 1 minus epsilon. You go to the third state, same deal, epsilon probability of making a mistake, and so on. So you have capital T of these terms that all look like 1 minus epsilon to some power times epsilon times t minus something. So each of these terms in the sum, assuming the 1 minus epsilons are on the order of 1, meaning the epsilons are small, each of these terms in the sum are on the order of epsilon t. So we're just disregarding the 1 minus epsilon things because we assume epsilon is small, which means that 1 minus epsilon is close to 1. So all these terms are on the order of epsilon times capital T, and there are capital T of these terms. So that means that the bound that we get from this is going to go as epsilon T squared. If you want to actually calculate the number, it's like epsilon T squared over 2 because it's like a triangle because you're subtracting 1 every time. But in big O notation, that's epsilon T squared. And that is bad because it means that as the length of the tightrope gets longer, the number of mistakes increases quadratically. So that's a very bad loss. You'd expect that if the tightrope walker was a good tightrope walker, it would scale linearly. OK, does anybody have any questions about this derivation? Yes?
So for the assumption, the expectation is smaller than theta. Is the expectation over S or expectation over C?
In the assumption?
Yeah.
So there's no expectation in the assumption. This is important. This is going to change on the next slide. But here, the assumption is actually a very naive assumption. It just says you've memorized the data. It doesn't say anything about generalization. So it's just saying literally on the states that you trained on, your probability of making a mistake is less than or equal to epsilon.
Oh, I see.
It's a very simple assumption. Yeah. Any other questions? OK. So this was really kind of a warm-up. The real result is the one that's on the next slide. Because the trouble, well, actually, maybe one of you guys could tell me. What do you guys think is the trouble with this kind of analysis, especially with this sort of assumption? Why might this be very unrealistic for any reasonable situation? Yeah?
You're usually more confident than just only on the states I've trained on that have this tiny probability.
Right. So the answer, for those of you that didn't hear, is that it's a little bit unrealistic because you have some confidence about getting the right answer, not just literally on the states you trained on, but probably on other states that are similar. So if you train an image classifier on like 5 different kinds of dogs and 5 different kinds of cats, it might classify other dogs and cats, not just literally the same exact pixel images. In fact, the whole reason that we use machine learning is so that we can train on one set of data points and then generalize to another set that comes from the same distribution. So this analysis is basically not making use of the most important thing in machine learning, which is generalization. And the simplest kind of generalization says that if your training data came from some distribution, then you will do well on other data points that came from that same distribution. And that is not being used here. So let's try to put that into action. This will make the analysis a bit more complicated, but this is the real kind of analysis that people would actually use. So before we had this very naive assumption that you just do well on literally the states that you've seen. Now we'll revise it to be less naive. We'll say that you do well on states that come from the training distribution. So for states sampled from P train of S, your probability of making a mistake is less than or equal to epsilon. But for states that were not sampled from P train of S, all bets are off. Now, of course, at this point, you might sort of think, well, OK, if you just got a state, how do you know which distribution it came from? Well, that's up to the person writing the proof to analyze. So you can argue that a certain state that came from some other distribution kind of looks like a state that would have come from P-train, but we have to show that. And that's, in fact, what we're going to do. We're going to argue that for some other distribution, you might actually get states that look like states from P-train. So we'll see that in a second. But before we go through the complicated analysis, I'll first go through the really simple analysis. The really simple analysis is actually for Dagger in this case. So with Dagger, remember that the whole point was that P train approaches P theta, right? So the distribution of training points, once you do this aggregation stuff that we talked about last week, becomes essentially equal to the distribution of states that you see when you run the policy. So if this happens, if P train essentially becomes equal to P theta, then can we actually bound the total expectation of the total cost? Does anybody have any thoughts about how we could do this? So here we're assuming that Dagger worked and it made P train equal to P theta. And this is an expectation under P theta. Any guesses? Yes.
It'd be similar to the sum from before, except if you fall off the tightrope, your chances of making a mistake are still epsilon.
That's right. So since the distributions are the same, even if you fall, you sort of assume that Dagger has collected data and lowered the chance to epsilon. So what do you think the bound will be then? So let's think about it like this. What's the probability of making a mistake at each time step? Yes? Epsilon. And how many time steps are there? T. So what's the bound? Epsilon times t, that's right. So you basically assume that you never end up seeing out of distribution states because you made the distributions equal. So that means that every single step you have epsilon probability, there are t steps, so epsilon t. And this is the best you could ever do, because unless you eliminate the probability of making mistakes altogether, you will always have some non-zero probability at every time step, and you have capital T time steps, so epsilon times t is the best bound you could ever hope to get. All right, so that's the easy part. Now the hard part is to analyze behavioral cloning. So for behavioral cloning, p train is not equal to p theta. So here's what we're going to do. I'm going to write lots of scary equations, but I promise I'll explain them. And if you don't understand those equations, then please ask. If you want to see this written out, check out this paper. This is the Dagger paper, a reduction of imitational learning and structured prediction to no regret online learning. So if p train is not equal to p theta, here's what we can do. We can actually express, there's a little bit of kind of mathematical sleight of hand here. We can express the distribution of states at time step t. So when I write p theta of st, this is the distribution of states at time step t. So t steps along that tightrope. I can express this as a sum of two terms. And this is a little bit of a silly sum. So the first term, this is basically what happens if you never make mistakes. So your probability of not making a mistake is 1 minus epsilon on the first time step. And then if you didn't make a mistake, then you stay in distribution because the action you took is sort of indistinguishable from actions that the expert would have taken. So then at the next time step, your probability of not making a mistake is again 1 minus epsilon. So for t time steps, you have 1 minus epsilon to the t as the probability that you've basically done everything right. There might be other ways to do everything right. Maybe you made a mistake but then recovered. That's not accounted for here. But we know that your probability of doing everything right is at least 1 minus epsilon to the t. And if you did everything right, then where you're at time step t is indistinguishable from where the expert would have been. So that means that you can say that you have a 1 minus epsilon to the t power probability of finding yourself in a state at time step t that is indistinguishable from the state that you would have gotten in a p train. And then there's the other part. So 1 minus epsilon to the t, that's basically the rest of the distribution. And that we don't know what it is. Like that could be something complicated. Maybe you fell off, maybe you got back on, maybe you fell off and then like, you know, hurt yourself. All sorts of crazy things might have happened. We don't know, so we just call that p mistake. Now it could be that some parts of p mistake also look like p train, but we just can't be sure. So pessimistically, we can say that we know for sure that you're going to have at least a 1 minus epsilon to the t component that is indistinguishable from p train, and the rest of it, 1 minus epsilon to the t, is some unknown part that we're going to call p mistake. And this way of breaking up p theta st is crucial to our analysis. So once we break it up like this, we can show kind of an interesting bound. So okay, this first part is a probability we made no mistake. This is some other distribution. And the interesting relationship that we can show is that we can analyze what's called the total variation divergence between p theta st and p train st. So let me write some of this out on the board. Whenever I use an expression like that absolute value, whenever I write p, can everyone see this? Yes? Okay. P theta st minus p train st. This is just equal to the sum over all states of the absolute value between those distributions. So I just drop the sum essentially, and this is what's called total variation divergence. Okay. So now where does that relationship come from that I have on the slide? Well, the place where it comes from is I'm going to take this p theta and I'm going to substitute in the equation above. So I'm going to write it as 1 minus epsilon to the t p train plus 1 minus epsilon to the t p mistake. And then this bit, that I'm going to write in a similar way as 1 minus epsilon to the t p p train plus 1 minus epsilon to the t p train. Okay, that's kind of a silly thing to do because these two terms sum to 1, so of course you add two things that sum to 1, you get 1 times p train, right? And now this term and this term, they're the same, so when I subtract them, they both go away, which just leaves this thing times p mistake and this thing times p train. Now, since I know that 1 minus epsilon to the t is positive, I can take that outside the absolute value, which gives me the right-hand side of that equation. So I have this thing minus this thing, absolute value of that, take this thing outside the absolute value, and I just get 1 minus epsilon to the t times the absolute value of p mistake minus p train, or p train minus p mistake, whatever you want to call it. So that's the equation there. Any questions about this? OK. So now what we can do is we can bound this quantity. So we don't know what p mistake is. We don't know how similar it is to p train. So the worst, the most conservative bound that we can put on there, the one that we're really sure about, is to simply replace the absolute value with the worst thing that it could be. What is the worst possible total variation divergence that we can have? I mean, you can kind of see it on the slide, but I'm going to ask you to explain your answer. 2? Why is it 2? Yeah? Right. They're probability distributions. They sum to 1. So that means that the most dissimilar probability distributions you can have, if you imagine it as like a histogram, maybe this one has like, all of its mass over here and nothing here, and this other distribution has nothing here and all sorts of stuff like over here. You know that this sums to 1 and this sums to 1. So over here you have like 1 minus 0, and over here you have 0 minus 1. Take the absolute value of all of those, and the sum of these absolute values has to be at most 2. So that means that anytime you have total variation divergence between two distributions, it's bounded by 2, if you basically know nothing else about how similar they are. So that means that we can replace that absolute value by 2, which just leaves 2 times 1 minus epsilon to the t. Now, we don't like dealing with exponentials in our bounds because that makes it hard to really say nice, concise things about what's going on. So we can use a nice little identity. Whenever you have this something like 1 minus epsilon to the t, if you know that epsilon is between 0 and 1, you can actually show that 1 minus epsilon to the t is greater than or equal to 1 minus epsilon times t. And if you have 1 minus epsilon to the t, you can flip the inequality around. That gets rid of the 1, and then you can show that this is less than or equal to 2 times epsilon times t. And this is a bound that we can work with. That's saying that the total variation divergence between p theta and p train at any time step is linear in t, and also linear in epsilon. So now we can actually use this to work through a bound on our cost. So let's do that. So our cost is the expectation of the sum of the costs, and we can, by linearity of expectation, we can push the expectation inside the sum. So we just sum over all the time steps, and we take the expectation under p theta st of the cost at time step t. We can write that out just with the definition of an expectation as the sum over all the time steps of the sum over all the states of the probability of that state at time step t times the cost of that state at time step t. And now, the trouble is, of course, we don't know the expected cost under p theta, but we do know the expected cost under p train. What's the expected cost under p train? Anybody want to volunteer an answer? For a single time step. Epsilon, yeah. It's epsilon, because that's exactly what this assumption says. So basically, our goal is to express this thing in terms of an expectation under p train and something else that we can bound. OK, so let's try to do that. Here's what we're going to do, and I'm going to work this through on the board. So first, to unpack this a little bit, there are two terms. There is a term that is an expectation in terms of p train of the cost, and there's some other term that has some other stuff, and there we don't know how to express the expectation of the cost with respect to this, so we just use the worst possible cost, C max. What's the worst possible cost at a single state? You can call it out. 1, yeah, because we're using the 0, 1 loss right up there. Okay, so let's make sure that we derive this, because we want to make sure I didn't make a mistake on my slide. Okay, so what we're going to do is we're going to say that, and I'll be pretty loose with my notation. When I write p theta or p train, I mean p theta of st, right? But I'll just drop the st just so I can write this more quickly. Okay, so p theta is equal to p train plus p theta minus p train. Everyone's good with this? You add something, you subtract it, you get back the same thing, right? So that means that if you have p theta times the cost, that's p train times the cost plus p theta minus p train times the cost, right? So we just multiply everything by the cost, and we group these two terms together. Now, whenever you have a difference of two things, you know that that's less than or equal to the absolute value of that difference. So we can do p train times cost plus absolute value of p theta minus p train times c. And these c's, you know that they are always less than or equal to 1, which is c max. So that means that you can also write this as less than or equal to p train times c plus the absolute value times c max. Okay. And now we have exactly what I have there on the slide. Does anybody have any questions about this? Okay, let's continue. At this point, we actually have everything we need to derive our bound. So this first part, the sum over st of p train times c for a single time step, what is that going to be bounded by? Epsilon, right? Because this is just the expectation under p train of c. So this part is epsilon. This part right here, the absolute value, what is that bounded by? Yeah, 2 epsilon t, just this thing. So you just take that, put that in there. C max, that's 1. So you can basically disregard that. So that means that this is a sum over t of epsilon plus 2 times epsilon t. And now, of course, we're in trouble because we're summing over t. So this is unfortunately epsilon capital T plus, order of magnitude 2 times epsilon t squared. So now we're back to our familiar epsilon t squared bound, which is bad news, but the unfortunate truth of all this. So that is the kind of the real derivation for why behavioral cloning can be problematic. Does anybody have any questions about this? Yes.
Could you go over again summing out over the STs?
So going from this to this.
Yeah.
Okay, so summing over the STs works like this. This part, basically the sum of this is the expectation under p train of the cost. And we know that under p train, our probability of mistake is epsilon. So this expectation here is epsilon. The second part is the sum with respect to st of this bit. So the c max is just 1. So we really only care about this absolute value difference. And that's precisely what we're analyzing over here. So here we show that the absolute value difference is less than or equal to 2 times epsilon t. So this bit is just 2 times epsilon t. Do you have any more questions about this?
No.
Okay. Any other questions? Yes.
So, I mean, look at our assumption. I kind of feel like this assumption is really strong because, like, the pi theta thing is a function of s, right? And this function is smaller than the constant. It means that we need to memorize our sample so well that from every sample from that distribution, we didn't make a mistake. But would it be better that, like, put another expectation over s so that, I mean, you will never memorize sample in the expectation set,
Yeah.
not in the
Right. So the comment, and this is a very valid comment, was, okay, the assumption, as I have written here literally, it's sort of needlessly strong because it's saying, like, for every state that you sample, you have less than epsilon. We didn't actually ever use that assumption. All we actually use is the fact that this expectation is less than or equal to epsilon. So it could be that there are some states under p train where you always make mistakes and some other states where you never make mistakes. So all you really need, if you want to be precise about, is you need to assume not that for every state the mistake is epsilon. What you really need to assume, the minimal thing, is that the expectation with respect to ST of the pi theta AT not equal to pi star ST, given ST, that this thing is less than or equal to epsilon. And that's actually a weaker condition, because that's not saying you make mistakes with probability epsilon in every state. That's saying that in expectation over all the states, the number of mistakes is bounded by epsilon. And that's actually the only thing you really need for that proof to hold. Any other questions or comments? OK, so that's it for the theoretical analysis for imitation learning. At this point, I'm going to switch over to Kelvin, who is going to provide a tutorial on TensorFlow, which will hopefully be useful for your homework. I'll help you get set up. Do you have HDMI?
All right, cool. So everyone, I've talked to some of you in my office hours, but my name is Kelvin. I'm one of the GSIs for the class. So in this lecture, we're going to go over an overview of TensorFlow, which is a computational graph library that many of you may have already seen if you've downloaded Homework 1 and have looked through it. So the overall goal of this kind of mini lecture is to get you guys familiar with kind of like the bare basics of TensorFlow. There's a lot to learn about it, but this is going to just be like the core knowledge that you'll need in order to do the homework. Cool. So why are we doing this lecture on TensorFlow? So just a reminder, the goal of this course at a high level is to train agents to perform some kind of useful task. And so what that means in the context of deep reinforcement learning is that we're going to have some data that we're going to collect through some process. From that, we're going to train some kind of model. And then we're going to give this an agent, and the agent will go and get more data and do something useful, hopefully. So this lecture focuses on just this aspect of this branch. So how are we going to train these models? So how we're going to train them is essentially we're going to use TensorFlow. So just a reminder, the problems that we're going to look at from just a purely computational perspective are going to look something like we have a function approximator, which is in this case f of theta. We're going to have some data set, which is D, which is going to be composed of many examples, for instance, x and y. And we're going to be looking for a set of parameters that make some kind of loss, some kind of norm, some kind of cross-entropy loss low. What is TensorFlow? So TensorFlow is basically a library for defining computational graphs. So I'll explain what a computational graph is in a second. But the main benefit that we get from TensorFlow is that we're able to compute gradients very quickly. And a lot of the learning that we're going to do is going to be based upon some kind of gradient-based approach. And so this is going to make this just really easy. So just to illustrate kind of what a computational graph is, I'm just going to quickly erase this. I think one common analogy that people use is that making a computational graph is similar to doing math in a very abstract sense. So if you have written neural network libraries before, you might have had some kind of example where you perhaps had some input x, and then you might have used libraries such as NumPy to define some kind of dot product with a weight matrices and x. You might have added some kind of bias, and then you might have for instance used some kind of nonlinearity. Okay. So this might be one line that you might imagine in some kind of neural net code base. So in TensorFlow, you're basically going to define this as an abstract graph. So wherever I've written NumPy, you can replace it with TensorFlow. And then this graph is going to be able to be reused at different parts of your code. So your code is going to kind of exist outside of this. Your graph is going to be defined, and you're going to be able to reuse this graph for many computations. Are there any kind of high-level questions of what exactly this means? OK, cool. So in the context of neural nets, so imagine you have like a network that you want to implement. So this is a very simple 2-layer network. How we would kind of define this mathematically is that we would have like an input x. We would multiply it by some kind of weight matrix that represents the connectivity. We're going to apply some nonlinearity, and we're going to do this over and over until we get an output layer. So then how do we find like the set of parameters that actually will give us a low loss? Then we could just ask the question like, what gradient should we follow for like the weight matrix W? And then continue doing this backwards all the way to the last weight matrix using what is referred to as the backpropagation algorithm. And so basically what TensorFlow is going to let us do is that we're going to just be able to define this top line here of what like H1 is, what H2 is, and what the final network is. And TensorFlow is going to calculate all the gradients. So if you guys are really interested in learning the backpropagation algorithm, you can just look it up online. You can also look up some resources from CS285 Fa19. Or you can post in Piazza, and perhaps we can like point you to some other pointers. Cool. So there are many people who have very strong opinions about like which library they use in terms of like, do you use TensorFlow, do you use PyTorch? Everyone has something that they like. I just want to point out that they're fundamentally all kind of the same kind of library. If you learn one, if this is like the first time that you've ever used one of these libraries before, you'll be able to learn any of these other ones really, really easily. So don't worry. And if you know any of these other ones, and every year there seems to be another one that comes out, it'll be really, really easy for you to learn TensorFlow. OK, cool. Are there any other questions? Or any questions at all? OK, great. So now we're going to move on to a little Jupyter notebook. So this is going to be made available online. You just follow along on the board, and if you have any questions, let me know. So first of all, we're just going to import our libraries, make a little helper function. So yeah, so what is TensorFlow? So here's a basic example. So TensorFlow you use to basically define a series of, oh, sorry, what's the question?
Zoom in a little bit.
Oh, sure. Does this help? Is that better?
Thank you very much.
OK, cool. So what is TensorFlow? So you're basically defining some kind of computation. So in here, in the example, we're creating like a session object. So session object is kind of like a TensorFlow abstraction that kind of encapsulates all of your computation. It manages resources like how many GPUs you're using, how many CPUs you're using, things like that. But that kind of you can worry about. We'll talk about a little bit at the end of the lecture. But the main kind of core purpose of TensorFlow is to allow you to find things that are, for instance, like constants, define some operations, for instance, adding them, and then basically be able to like use this session to run this computation in order for you to get a result. So if we run this little cell here, we can add A and B and get C, and the answer is 3. OK? So this is a pretty simple, basic example. So the first thing that we're going to cover is essentially how to input data. So if you basically had to kind of create constants every time you had a new set of data, this would be extremely annoying. So this is like the example of that. So instead, what we can do is we can define what are placeholders. So placeholders will just be like an abstract node, which you can think of as your data, either your data input or like a label. And from there, you're just going to be able to kind of at runtime feed in a value and reuse the same computational graph over and over. Were there any questions? All right, feel free to interrupt me, by the way. So in order to define a placeholder, all you have to do is give it like a data type. So in this case, we're using float32. You give it a shape. So here we're going to use scalar, so we're going to use 1. And you can give it a name to make it a little bit easier to figure out what's going on if you run into any errors. So we're just going to go over the same operation. We're going to feed in 2 values as before. And as you can see, in one case, we fed in 1 and 2, and we get 3. In the second case, we feed in 2 and 4, and then we get 6. So this could be like a new set of data, something else. So this kind of provides like a little bit of a convenient way of inputting variable data. OK, are there any questions? No? Great. So one question you might have is, what if we don't know the size of the input beforehand? So TensorFlow allows you to specify a shape to be none, which basically means that you're not going to actually give it a shape. And that shape is going to be determined at runtime. So in this case, this is kind of like the exact same example. But in one case, we're feeding in a scalar value. And in the second case, we're feeding in 2 vectors. So if we run this cell here, you'll notice 2 things. First, if we try to examine the shape of these placeholders, we're just going to get a question mark because you don't actually know what the shape is prior to running the data. And in the second case, when we run them, we're going to either get a scalar addition or just a simple vector addition. Okay, cool. So the reason why this is like a useful thing is that very often we're going to be dealing with variable things like batch sizes. So the first dimension will not be known ahead of time, so you can put something like none. And then at runtime, you can kind of define whatever batch size makes sense for you. Cool. Are there any questions? All right. So how do I perform computation? All right. So so first of all, so now that we have some like input data, and when we want to perform some useful computations, we can do simple things like, as before, just examine the values. In this case, we can do like slightly more complicated things like run addition with the values that we've defined before, and we can do things that are actually a little bit unintuitive. For instance, we can add two vectors that are of different shapes. And one thing that I think is worth looking out for is that TensorFlow tends to follow broadcasting rules. So if you guys are familiar with libraries like NumPy, it'll do things like copy over arrays if the shapes are not matched. And this can kind of actually produce undesired behavior if you're not super careful. So this is just something to look out for. So the broadcasting kind of effect is kind of useful in a lot of settings. So for instance, just to explain broadcasting, if there are two arrays that have different sizes, TensorFlow will automatically try to match them by filling in the shape of certain arrays. So like a very simple example is if I have like a vector and it's, for instance, like a bunch of different data points, and I want to add like a scalar value of 1. This thing here will have some kind of dimension like 5, 1, and this will just be a scalar here, so just 1. And so TensorFlow will copy this 1 over and add it to each of these values here. So this is a kind of trivial example, but for instance, if you're trying to do very common things like normalize a bunch of activations or do some kind of standardization, this can be very convenient because you can just normalize across your entire batch using just like a very, very simple operation. But this is something to look out for because, again, if you're a little bit not careful, these bugs can be really hard to catch. OK. Are there any questions? Cool. All right. All right. So some other things that we can do instead, so an example before is we can use some libraries that TensorFlow has defined to do things like do matrix multiplication. So one other thing to look out for is that while you can use Python things like multiply using like the little like star, if you want things like matrix multiplication, you have to be a little bit careful and sometimes look into the documentation to make sure you're not doing element-wise multiplication as opposed to matrix multiplication in some sense. So in this example here, I basically have two examples where one I'm doing a matrix multiplication and one where I'm doing just an element-wise multiplication. So in the second case, you're going to get essentially this broadcasting effect, and the second one is just going to be a dot product. So it'll all come down to like -14. All right. Any questions? All right. So the final kind of point of TensorFlow is that you can chain these operations together symbolically. So you don't need to like run it every time in order to get your data and then remake another computational graph. You can actually just stay in like TensorFlow land and continue to like use like all of like the TensorFlow abstractions and chain them together. And this is basically how we're going to construct neural nets. So in this case, taking B, I'm adding it to itself to get C0. I'm adding 1 to it, which is actually using this one. And after running it, we can get like different results for it, or we can get a different result for it. Okay. Are there any questions? Cool. All right. So the other thing is that TensorFlow has a bunch of operations that you'll probably need throughout the course, things like taking means, computing standard deviations. It's pretty easy to just Google for things and find them if you don't want to like reinvent the wheel every time you need to create an operation. So there's not too many of these operations in general. So for instance, this example of taking a mean over a vector, I do recommend that you go through it in general so that you don't like reuse or try to recreate something that already exists. Cool. Is there anything unclear so far? Just out of curiosity, how many of you guys have used TensorFlow before? Okay, so about half. How many of you guys have used like a different computational graph like Torch or something like that? Okay. So I would say like the majority of you have used one of these. Okay. All right. Okay, so the next step that you might want to do when you have to create, like, for instance, like a neural net is that you might want to do something like create a variable. So in TensorFlow, you can create constants, but if you want like a free parameter that you can change all the time, instead of creating a constant that we have here, we can instead create a variable. So in order to create a variable, one of the abstractions, there are many abstractions actually provided by TensorFlow, but one of the abstractions provided by TensorFlow is to use the getVariable abstraction. So all you need to do there in that situation is provide a name for the variable. And this is actually kind of important because the names are actually kind of, they're essentially the keys in the graph, so they can't be duplicate. And unless you wanted to, of course, share weights, you need to provide a shape, the data type, and finally you need to give like an initial value for the variable. So here I'm using a constant initializer, but there's a bunch of other initializers that we'll go over in a second. And so one very useful thing that you might want to do is actually be able to check to see what variables you've created, because sometimes you might think you've created a variable, but you may not have actually in reality. So one thing you can do is you can, every time a variable is created, it gets added to a big dictionary, and you can kind of look it up. Sorry, there's a question?
Yeah, what was the purpose of calling, because in a lot of other ones where you like define a constant and you do session.m, why at the very top do you do TensorFlow.session?
Oh, okay. So here, so basically, I defined this like kind of little helper function at the top. So this is actually not a TensorFlow abstraction. But basically, every time I was running these sessions, so a session kind of encapsulates the graph. So if you want to have separate graphs that kind of encode separate computations, you need to reset the graph. So this was just kind of like, since for didactic purposes, every time I'm like kind of running one of these new cells, I don't want to like reuse the old graph. I'm just resetting it. But in practice, you rarely have to do this because you'll define one graph and you won't need to like constantly destroy it and recreate a new one. That's a good question. Thanks. Were there any other questions? Cool. All right. Let's just go back down here. Okay. So yeah, so now that we've kind of talked about variables, basically what we need to do is do things like add them or like whatever we need to do in our graph. So for instance, this is just adding your variable to C so you can use it later. So another example is, for instance, if we want to run the initializer. So here, one thing that is also kind of useful in TensorFlow is that every time you create a variable, its initializer is also added to this key of kind of global initializer. So you can retrieve that very quickly with the TF global initializer, and then from there just run the session. So here, this allows us to kind of initialize this variable. So if you recall before, we had this like constant initializer, but and after we run the init op, we're able to kind of retrieve the values that are in there. So this is kind of an important point because if you don't initialize your variables, you can't actually use them. Yeah.
Are the initializers just like all zeros or random?
Yeah, so you can, so TensorFlow actually provides a lot of abstractions for like common random initializers that are kind of considered good initializations for neural nets. There's also constant initializers. There's also like kind of more wacky ones in case you need them. Yeah.
So what's a good one to start with?
So I think a very good one to start with is something called Xavier initialization. So it's a very common initialization for, I mean, you can use it for tanh nonlinearities. You can use it for nonlinearities. Those are for like the weight matrices. For the kind of biases, you can often just initialize them to be very small values or just 0. That's fine. Yeah. All right.
Why would you want to use variables instead of just putting placeholders and then passing values?
Sure. So the placeholders I like to think of as kind of like the inputs that will change at every time you run the graph, whereas the variables might be something structural part of the network, so like the weight matrices. So those things do need to change, but they're like part of the network, and you may not want to like constantly be like inputting them into the network. That's a good question. Thanks. Yeah.
Does the initializing global variables function,
Mm-hmm.
what does that have to do with scope?
The-
You said I saw a
Mhm.
thing called
Okay, so scoping in TensorFlow is like one way of kind of very conveniently organizing your variables. So you can create variable scopes where essentially you create this kind of like context which allows you to, every time you create a variable, it's like organized within this scope. So the global initializer will grab all of the variables in your graph or your default graph and like take all of those operations and put them into one macro operation. So when you run it, you initialize all your variables. But for instance, if you just want to initialize variables within a scope, you need to retrieve just those initializers and initialize them. But that's not, I mean, that is kind of a more advanced use case, but it's not something we're going to encounter in, like, for instance, in like homework 1. That's a good question. Thanks. Were there any other questions?
So if you run local variables initializer in a particular scope, it would only do the variables in that scope?
Yes. So you need to, so there's a specific name that you might have to look up, but you're able to actually retrieve basically initializers within a certain scope. And this would, like, for instance, let you just like reinitialize a part of your network if this is something that you need to do, while keeping the other ones like to be whatever value they were prior. Cool. Are there any other questions? All right, so so now we're just going to go through a simple example, like a little toy regression problem, which will illustrate like a bunch of the concepts that we've kind of gone through and put them all together and let us train like a really simple network. So first I'm going to create some like fake data. So this is just a noised sinusoid. This is going to be our data set. OK, cool. So I'm going to go through all of this. This is like a little bit dense, but I'm going to go through it line by line. So I'm just, again, resetting the session. You probably won't need to do this, but we're going to just create a model. So we're going to create 2 placeholders. So in this class, we're just going to do a toy regression from an x coordinate to like a y coordinate. We're going to define the data types, and the shape is going to just be the batch size and 1, since it's just a scalar value. And so to create our network, we're just going to create like a bunch of random variables. And so we're going to create 3 kind of weight matrices. And we're going to use the Xavier initialization that I just mentioned. You can use something else, will probably still work. And then we're going to create 3 biases. And then we're going to also just initialize those to be 0. So right now, here we just have a bunch of placeholders, and we have a bunch of variables that are going to be the the weights of our network. And from here, we're just going to kind of chain these all together, like very succinctly, to get us like a network. So on the next couple of lines, I'm just organizing all of these different things that we've just created. One of the things that we're using are these like ReLU activations. So there's a bunch of different ones that you can look up in like the documentation, but for here we're just going to use ReLUs. And so now to get into like the actual creating of like the neural net. So very succinctly, this is just what it is. So we're going to start off by just running through all our activations, like looping through our weights and biases and activations. And at every point, we're going to take the previous layer, multiply it by a weight matrix, add our bias, and then make sure that if our activation is not none, just apply that activation and do this loop until we're out of activation. So it's a very simple loop. And so, yep.
Is there any reason you couldn't use tf.layers.nets?
Yeah, so there are a bunch of these abstractions that you can use, and this would, like, for instance, the tf.layers.dense is just going to give you, it's going to create the variables for you and like help you do this management for you. So in the homework, actually, you're encouraged to use things like this. But it's kind of good to know under the hood, like all of these like complicated libraries, or I mean, in some cases, they're not that complicated, basically rely on like the basic mechanism of TensorFlow. So you could do this, and some people actually create their own dictionaries and own abstractions, but you're more than welcome to use any of the things that exist in the library. Cool. So at the very end of creating this computational graph, we're just going to have our output, and just we're going to return a bunch of these things. And in the outer context, after we call this model, what we can do then is basically compute our loss function. As before, as above, we created a bunch of placeholders for our labels, which is our true values. Our network right now in the output underscore pred variable is containing our prediction from our model. So again, this is all in like a TensorFlow abstraction land. And then we're going to just multiply it by 1/2 and then take the mean, and that's just going to be our loss. So this is just MSE. So it's pretty straightforward. So one thing that I think I should point out is that I think a common maybe mistake for someone who's never used these libraries before You might think like, oh, can I use, for instance, like NumPy operations and combine them with TensorFlow in areas that might seem like convenient? And the answer is no. So once you start using these TensorFlow operations, you can use like certain overloaded Python operators like multiplying and adding, but you can, for instance, like start combining NumPy arrays. So everything has to be in TensorFlow land once you start doing TensorFlow. Okay, cool. So now that we've defined our loss, we just need to optimize said loss. So the simplest way to use this is to use one of the optimizers that's provided by TensorFlow. So if you're not familiar with the Atom optimizer, it's fine. That's just a very common momentum kind of quasi second order optimizer that people use. There are other optimizers like SGD and SGD with momentum. If you actually go into this tf.train documentation, like a bunch of these have already been implemented, so it's pretty easy to kind of swap these in and out and try them all. So after this, we're going to create this optimizer. So you basically, this line here is first creating the optimizer object, which is its own thing, and it's going to then call minimize on our loss. And this is going to create an opt, like an operation, that's just going to run one step of the optimization. Okay? Are there any questions? All right, cool. So this is basically like now at this point we're more or less done creating the graph. So this is all we need essentially. We have something in our graph that's able to produce outputs. We have something in our graph that's able to minimize our loss. And now basically all we need to do is plug in the real data. Okay. So from here, what we're going to do is we're going to initialize our variables. So this is calling the global initializer. We're going to create a saver. So very often you're going to need to like dump your weights and reload them. And so there's an abstraction for that as well. And then we're just going to run training. So training, for those of you guys who maybe are less familiar with how to train networks, looks something like you sample a batch of data randomly. And then from there, you're going to pass it through your network and run optimization. And then you're going to do this over and over again until you've reached some kind of convergence criteria. Yep?
How do you pick your batch size?
How do you pick your batch size? Those are really good questions. So, I guess maybe one question that's also worth considering is like, why do you have a batch size? So the reason why we don't use a batch size, for instance, of 1 is that if you have like hardware like a GPU, you can run everything in parallel. So this basically allows you to speed up training really quickly. So batch size, of course, is like kind of just like a hyperparameter, so you have to choose it. So in a sense, you're sometimes trading off essentially how fast you're going to be able, how fast you're able to do things in parallel. So if you choose a huge batch size, you're able to, for instance, just like go through your data a lot quicker. But it also interferes with other things like your learning rate, for instance. So if you have a very big batch size, you're able to get a very good estimate of your gradient. So then that's going to let you, for instance, like take a bigger gradient step in theory. Right? So in practice, like what you would do instead is you would kind of choose as a hyperparameter. So you can like try different batch sizes. But you should just keep in mind that if you're looking at your overall performance, it actually interacts non-trivial with like other things like how your optimizer works. That's a good question. Was there anything else? Sorry, did I answer your question? I guess. Okay, great. All right, cool. So we're just going to loop through our training data. In this example, we're just going to sample some indices, pull out our data that we're going to try to train on, and then we're going to optimize our model and get the MSE. So one thing that's, I think, really good practice, so in your homework, for instance, is to monitor your loss. Because sometimes, like you, for instance, may have thought that you actually set up the model correctly, but if you look at your loss, it might not be going down, or it might be exploding or anything like that. And this can give you like, kind of hints as to what's going wrong in the overall optimization. So for instance, if your loss is exploding, this might be a sign that you're using a learning rate that's like way too big. Or if the loss is not changing at all, this might mean that there's something kind of broken in your graph, or maybe gradients aren't flowing very well, or gradients are vanishing. So these can kind of always give you like little hints as to what's going on. So now that we're doing that, we're just going to train this model. So now I'm just printing the time step and like the MSE. So luckily we've set everything up correctly, and the mean square error drops to something like rather low. And then from there, so once again, don't reset your session object. Or I guess in this case, I did, but I reloaded my weights. But if I didn't reload my weights, everything would be reinitialized. But I'm able to essentially be able to do some type of prediction. So this was like the old data that we had, and the red line is the predictions that we got. So we got pretty close, is like long story short, with this like simple 2-layer network. Cool. Are there any questions? All right. So some tips and tricks. So here is another example here of broadcasting. So one thing that you should definitely check is to check your dimensions. So there is a big difference between doing things, having something that's a shape like 4, 1, and like the converse, which would be like 1, 4. So in this situation, for instance, you might think, for instance, that these two things don't actually add, but they do. So be sure to check things like that. Another very common thing that you're going to need to want to look into is to check what variables you've created. So one way to do that is look into like the global initializers and like look through things as well, and to make sure that like all the variables you created kind of make sense to what you intended to. So you don't, like, for instance, are accidentally reusing variables where you don't need to, or you've created variables where perhaps they're not being used, or doing something unintentional. So this is just like generally good practice. Cool. Are there any questions? Great. Okay. And so the other thing is that, like, if you generally have questions, be sure to like go through like the TensorFlow like API. Just like look up the help functions. This is generally like very helpful because in practice, like there's like a ton of these different libraries that use TensorFlow, and so be sure to like look through the like base documentation to make sure you're doing what you think you're doing. And let's see, finally, yes. So one other thing is that there's a bunch of these libraries that have been developed. Some of them are actually officially part of TensorFlow, so you can actually just use those directly. So for instance, this is like a module in TensorFlow in the contrib like library where it's basically implemented all of like the fully connected stuff that you need. So here, like you just pass in, for instance, your weights, and like you pass in like your activations and so forth, and from there it kind of does the entire like operation of doing one fully connected layer for you. There are many like such libraries. There's like Keras, which is very common. There's Slim, which used to be quite common, and all of these kind of perform functionally the same thing. But underlying all of this is like just the basic principles of TensorFlow that we talked about before. Cool. Are there any questions? All right. Oh yeah, and so finally, so this is a question that one of your classmates asked earlier, is a question of variable scopes. So you might think that like creating these like variables one by one can be like a tad tedious. So one like very simple way of organizing your variables is to use what is referred to as variable scopes. So with variable scopes, you create like these little contexts. So for instance, here you have like you create a context that represents layer 1, and then when you call tf.getVariable, it's going to actually create a variable that's within this context. And so we'll kind of see what that means in a second. So as you see, like all of these networks or all of these weights are being created in these contexts. But then when you go later on to examine what's in them, what you'll see is that they've all been kind of like neatly organized within like these little contexts, like within these little names. Cool. Are there any questions about variable scopes? Okay, great. And so finally, GPUs. So if you have a GPU or access to GPUs, this can definitely help speed up computation, especially later on when we work with things like ConvNets and images. So TensorFlow lets you kind of interact with this GPU at the level of abstraction of these sessions. So for instance, here, like we're creating like specifying a GPU device. If you have multiple GPUs, we're specifying how much of this GPU we want to occupy. And then from there, you can like create this GPU's option object. You can create this like config proto, which like kind of encapsulates all of these things. And then you can pass this essentially to your session object. So now your session object will have some kind of notion of GPUs. And this will like when you actually run the computation, you will need to think about like, oh, how is all this CUDA stuff working? Essentially, TensorFlow will take care of that, and you'll get results exactly as you expect. Cool. Let's see. All right. So the very final thing is TensorBoard. So I don't really have too much to say about TensorBoard as a thing. TensorBoard basically is like a very convenient tool that you can use to like visualize your results. So in the code that we've given you in homework 1, a lot of things like your loss, actually your loss might not be in there, but like a lot of the other metrics are kind of logged in TensorBoard format. So what you can do then is you can essentially just install this TensorBoard application, which is kind of part of like the larger TensorFlow ecosystem, and you can use this to kind of visualize your results. In the case of the stuff that we provided as the starter code for homework 1, there's also some video code, so you can actually see the policy like move through your ant around or something like that. In general, I highly recommend using these tools because it gives you a lot of insight as to what's going on, so you're not just staring at like a bunch of code running. You can actually kind of think about how the loss is interacting, how like, for instance, the agent is actually moving, and this can give you a lot of intuition when you actually use these things, not only in this course, but if you use these for any kind of like application that you care about, or if you go on and do things in industry, some intuition as to what is actually going on. Cool. All right. Okay, so that's actually all of the material that I wanted to get through. I think we're a little bit early, Sergey. So I guess were there any questions to finish up? Yeah.
Do you have any suggestions as to which architecture we start with?
Sure. So for the stuff that we're going to do in homework 1, we're just going to need things like fully connected networks. So you won't need it to, there's no, for instance, like images that we're working with, so we don't need to take advantage of any of the structure there with like convolutional structure and so forth. I would recommend for the first homework maybe like varying like the number of layers that you have. There's currently in the starter code it's set at a certain default, but you can change that to see how that interacts. I think maybe one point to make about training networks in the context of this course is that when you read, like, for instance, papers about neural nets in like big conferences, you'll see all these like architectural changes, these really complicated things. But with a lot of the models that we're going to use in this course, it's very sufficient to just have a very, very small model to do learning. This kind of is like maybe a little bit of evidence that for us, it's not really the capacity issue that we're trying to solve. It's more of like the search problem of figuring out what are the weights that we need for the task that we have, given like the signal that we have like in the context of RL. So that's really what is the challenging. Like we can't just like make the network like arbitrarily deep and arbitrarily complex and give us like necessarily better results.
So there's a default number of layers in the code somewhere. That's a good place to start. Is
Yeah.
there also a default size?
Yeah, so there's a default size as well. Generally, things that are like powers of 2 are like a good place to start. You can try like increasing the number of hidden units that you have in each layer, and you can try to see like how that affects learning and how it affects your overall performance. Yeah, cool. Were there any other questions? Yep.
TensorBoard question.
Yep.
What if you don't have like tabs? They're just not there.
Tabs are not there. Okay, so the tabs at the top, you mean these ones here?
Yeah.
Okay, so so in general, they should always be there, but in the version you may have, they might not appear if you're not logging any images. So I think the graph should be there almost always, because you'll almost always have something like that looks like a graph. But in general, I wouldn't worry. As if you're logging something and you don't see it, then there's obviously an issue. But that tabs component might not be that important because you don't always log images or videos or so forth. Yeah. Were there? Oh, yep.
Another TensorBoard question. Is
Yeah.
this something that we're going to, I saw that it was installed with the TensorFlow that we
Mhm.
installed. When we run the code that's in the starter code, are we going to automatically get this TensorBoard, or how do
Yeah.
we interface with it?
So the way the code is currently set up is that it's when you run like the script, it's going to create like a data directory, and each of the data directories is going to automatically like log all of the runs that you have. And so in there, it'll also create these like TensorBoard files that what you'll do is you'll just call like literally TensorBoard, and then you'll specify like a port on your local machine so that you can look it up in your browser, and then you just like point it to that directory, and that should be sufficient. Yeah. Yep.
You mentioned that we would have to run ComNets
Mhm.
images later.
Mhm.
Will we be provided access to a GPU?
Sergey, will it be provided access to GPUs?
I was hoping someone else would ask.
Oh, okay.
Give me the microphone. Otherwise you can't hear on.
Okay.
So unfortunately, we don't have any GPU resources that we can provide. That said, we have made sure that for the one place where you are actually required to use a ConvNet, you can train it on a CPU. It takes about 5 times longer, but you can do it in about 10, 12 hours to convergence. And you can debug your code without GPUs, of course. With a GPU, it takes about 2 hours. And that's only for the Atari assignment. That said, if you don't have a GPU, you can look around. I believe there's a way to get some free credits from AWS or from GCP, but it's definitely not required to actually do the homework.
Yeah, so for the homework, that will have some images. We'll also provide some environments that you can debug your code on to make sure that it kind of works, where you won't need a GPU. But in general, when you run like the full thing, it's going to take quite a bit longer if you don't have access to GPU. Cool. Yeah.
So can you say a few words about debugging TensorFlow code?
Sure.
You know what I'm getting at, right?
Yeah. So debugging TensorFlow code is generally a bit of it's a bit of a pain at times. So the reason why is that because like you very often aren't able to, for instance, inspect like parts of your graph. So one thing that, like, for instance, I do quite often is like I use the session run on intermediate computations to make sure that they kind of make sense along the way. The other thing that's very useful to do is that you can compute something like the gradient norm of all your weights, or look at the gradients of each of your weight matrices to make sure that the gradients are all flowing correctly. This is like generally a very good way of kind of debugging your TensorFlow code. Other things that you might run into, for instance, are like shape issues. Something that could happen is that you might multiply two things that are of incompatible shapes, and you'll get a very cryptic looking message. If that actually happens, what I really recommend you doing is you can actually go in and into the intermediate parts of like creating the graph, examine the TensorFlow variable, and then look at this, like its shape, for instance, and try to reason about why these errors are occurring.
Examine the TensorFlow variable means what?
So examining a TensorFlow variable would just be looking at, for instance, like all of like the built-in like shape properties, like the data type, things like that. Something that can happen as well is like things that happen with like data conversion. When you convert things from like integers to floats, you might have like different compatibility issues. These are all things to kind of look out for. So I think the fundamental thing that you guys should definitely be doing is like at every single point in time you should be logging things like loss and logging things like, for instance, like gradient norms. That's often very helpful. And if you see something that really doesn't make sense, you should investigate it. For instance, if your loss is blowing up, then your model is obviously not training correctly. And you can, like, even if you can't just like rerun your code multiple times and hope that it changes, you need to actually go into the graph and see if there's something like fundamentally going wrong. Cool. Yep.
What are the like 3 or 5 most useful things you should plot in TensorBoard?
Okay, the 3 or 4 most useful things that you should plot in TensorBoard. So the first thing I definitely think you should plot is something like your overall loss of your model. So be sure to, for instance, when you do homework 1, have something where you can make sure that your loss is actually going down. Some other things that for sure are useful to look at, or things I think I mentioned is like something like your gradient norm. So if your gradient norm is like extremely huge, that's an indication that your gradients are blowing up. If it's very small, it's an indication that your gradients are vanishing, so there's actually no learning signal. But you can also plot things in the context of like this course, since this is an RL course, you can plot things like your overall returns, like how many rewards you're getting, any interesting like metrics that like you think are like relevant to your actual problem. These are all things that can like be very helpful to gaining intuition about like your model overall. Cool. All right. Thank you very much. All right.
Just leave it. There's a